All right, guys. So today we're focusing on the rule breakers. Okay, so this is considered non-Mendelian genetics. If you remember me talking about Gregor Mendel, the father of genetics, he is the one that experimented with pea plants in his garden, right? And he was the one that came up with the dominant recessive patterns of inheritance and figured out that you receive, if you receive a dominant allele from the parent, that it's going to override the recessive. And the only way for the recessive phenotype to show is if you are homozygous recessive for that trait. So I just have a fun little meme here because when I was looking at Gregor Mendel over here, it reminded me of my favorite show, Dwight from The Office. But today we're going to be looking at the rule breakers. So the ones that do not follow that dominant and recessive pattern of inheritance. Now, remember, flowers reproduce sexually. So that is how Mendel was able to experiment with them. Remember, the pollen is the sperm of the flower, where the fruit is the egg. So bees, what they do is they spread, they're pollinators, so they spread the pollen around, and then what they will do is they make the offspring that they make would be the seed that grows into the new plant. Okay, so again, just take a look at the dominant traits for pea plants compared to the recessives, and that is all what Mendel experimented with. Okay, so today we're going to be looking at flowers as well. So I just want you to make some observations about sweet peas, camellias, and snapdragons, different types of flowers. So take a second and look at that. Okay, so you might have noticed that all the females in this case are red, which is correct, and all the males are white. Now take a look at the offspring, and I want you to think about what type of pattern of inheritance are they displaying. Okay, so this just looks like dominant versus recessive pattern of inheritance. And which one would be dominant? The red flower, very good. In this case, what do you think this would be an example of? If we cross a red and a white and end up with offspring like this? Very good. That would be an example of codominance because both phenotypes are displayed. And then in this third case, what would this one be? Very good. This would be incomplete dominance because you have a mixture or a blending in the offspring and a third new phenotype is created. Now, for I just already explained all that for you, so we'll just skip over that part. So now we're going to watch a little video.
By non-Mendelian, we mean that genetically they are rule breakers. They don't follow the regular Mendelian rule that having a dominant allele means the dominant trait will show. Remember in our guinea pig video, having a dominant allele represented by a capital H meant that the guinea pig would have hair? Only if there was no dominant present, a genotype of little h, would there be a hairless guinea pig. Well, that's a Mendelian trait. But we're going to cover now is when these traits are non-Mendelian and they don't follow these basic rules. So let's first start by snapdragons. We confess that when we heard this word, we thought they were some really amazing kind of creature. Well, they are amazing, but they're flowers. So I don't know, that's not exactly what we envisioned. Well, in snapdragon genetics, there can be three phenotypes: red, white, or something in between, pink. It's called incomplete dominance. In incomplete dominance, the dominant allele is not completely expressed when the recessive allele is around. There isn't really a clear dominant allele. If you cross a red flower, and we're going to write it here, big R, and a white flower, little r, you are going to get offspring that are big R, little r. But unlike a Mendelian trait, if this is incomplete dominance, that big R allele is not completely expressed when the little r is around. So big R, little r in this case is pink. If If you cross two pink flowers, big R, little r, like shown in this Punnett square here, you can get offspring that are red, white, or pink. Incomplete dominance is different from codominance. Codominance, like a co-worker, that prefix co should make you think together. They work together. The alleles, that is. For that reason, we like to use different letters entirely to represent the alleles. There is a codominance involving color in some types of chickens. Take a look at this Punnett square. If you cross a black chicken, represented here by BB, and a white chicken, represented here by WW, all the offspring here are BW. BW chickens are both black and white. They're speckled. See, both traits show up. This is the essence of codominance. And you know what's more awesome than a speckled chicken? Well, except for those silky bantam chickens. By the way, you will find that many people use different formatting for incomplete dominance and codominance. Some people like to use different letters entirely for incomplete dominance, and some people don't. Some people also prefer to do exponents with codominance, and some people don't. Formatting aside, when you're solving these Punnett squares, since we find this really does vary from classroom to classroom, the real concept is that in incomplete dominance, one allele is not completely dominant over the other. So you see this almost in-between phenotype. In codominance, both alleles are expressed. It's the application that matters here.
Okay, so again, you might see these genotypes and phenotypes shown genotypes shown a little bit differently, but the interpretation is what matters. And for I just want you to kind of go with how I'm teaching you to write these genotypes, because that's the one you most often see. So for sweet peas here, right? The phenotype options that we have are red, white, and then that's pretty much it. So remember, the type of inheritance would just be dominant versus recessive, like we were saying before. So to do the dominant allele, you would just use the first letter of the dominant trait, right? So we would use a capital R. And then to do recessive, you would use the lowercase r. Okay, and the only way that you're going to show the white flowers is if you're homozygous recessive, right? Now that's for sweet peas. Now for camellias, let's take a look. So the possible phenotypes is we have red, we have white, and we have red and white. So in this case, this would be codominant because you see the both phenotypes being expressed, right? Like if you had a co-teacher, both teachers are teaching you. Now in this case, that prefix co means to to cooperate together. Both are being shown together. So in this case, we use superscripts, okay? So for this one, since we have flowers here, we are gonna do, we could just do like the color of the flower. So how do I want to do that? We'll do like the petal. So the petal color, so I'll just do, or I could just do maybe like a P here. So for that one, red would be, you would be red. So the petal color, you'd be homozygous dominant for red, right? Now for white, for the petal, we would be homozygous dominant for white. Now for red and white, you would have one of each and you write them alphabetically as superscripts. Okay. Now let's look at our snapdragons. So phenotypes, we have red, we have white, and we have light pink. So in this case, this would be your incomplete dominance. Okay, and I'm not writing a definition because I'm kind of just telling you. So this is when, well, I could just, this would be both expressed. This would be like your blending or your mixture. Okay, so your blending results. So now if we're red, for this one we use all capital letters. So if you're red, you would be big R, genotypically speaking. If you're white, you'd be big W, and if you're pink, you would have an allele for each, so you'd be big R, big W. Okay, so we'll stop there for this part.